Hello everyone, I'm Manuel Gadi. I'm just recording this quick video with some highlights about fraud detection. So as a reference, you have these three files. So to start with, I'm gonna play with this data set here that is a credit card data set. And first of all, it's gonna hit restart and clear output so that I don't have any output in here. So I'm going to extend so it's a bit bigger. So it has to do with credit card fraud detection. So normally credit card fraud detection, the important thing is that the data is split between companies. So the merchant or the acquirer, the one that has the machine, it gets data from many banks and from Visa and MasterCard, but the brand Visa only have the Visa data and the MasterCard only have the MasterCard data for all the acquirers, but the bank, let's say Santander or Bank of America, only have the data for the bank itself. So it's quite interesting because the data nobody has all the data for all the frauds, and it's not shared. So, but it's quite interesting because all the three have different models to capture the fraud. So you can have an alert that the acquirer is saying this looks like a fraud. The Visa is telling it looks like a fraud, or the bank itself is telling it looks like a fraud. So when you get an alert as a bank, you can get alerts from these three types. And as a customer, you say, well, the transaction being blocked, but well, you're never gonna know who actually blocked it. It's normally the issuer, but the issuer may be getting the alert from the brand or from the acquirer. And this data that I'm playing with, it's a data that has many information like the merchant category code, so what type of category code it is, the previous transaction, it matters a lot, the zip code from the current transaction and the previous transaction, the transaction value, the amount, and the POS, what's the POS, what the type of the point of sale that transaction is taking place, the credit card limit, the brand, if it means a MasterCard, the type of credit card, if it's a gold credit card or if it's a simple credit card, the fraud score, that is it normally comes from Visa and MasterCard, the type of person, if it's a business or if it's a person, individual, the transaction national, so that's which country it is taking place, number of installments, if it's in installments, the transaction, and so on. So the speed, so the difference in time between this transaction and the previous one, the difference in fraud score with the previous one. So many variables, and the target variable. And the target variable, that is, it has been a fraud or it wasn't a fraud. So obviously this is a variable that comes later. So the transaction happens and then somebody goes there and label the transaction, okay? So just to have a quick understanding, so if we see this data set here, it has 3% of fraud, but I can tell you this data set has been resampled. It actually has been undersampled the majority class. The class that is not fraud has been downsampled. Why, or undersampled? Why? It's because the data set is so big that oversampling the minority class, the fraud cases, would take so long. I would make the data set so big that I decided to undersample the majority class, because the original percentage would be 3 fraud cases in every 3.8 fraud cases in every 10,000 transaction. We normally call it 3.8 basis points. And why do we do that? Because it's too complicated to be saying 0.038 percentage. So we're just saying in basis points instead. So what do you reckon? Is this is this imbalanced or not? Skewed or not? Yeah, very much skewed, right? And it's like finding a needle in a haystack. And to detect this fraud is going to be very complicated. And this one is transaction one. So we actually finding scheming, people that schemes copy that credit card and try to use it, or lost and stolen. So it's a transaction database. So we need to find those fraud. Why? Because the cost of fraud is very high. one transaction that we make money with, so like a simple, a normal transaction in credit card business, we only make like something like 0.5%, less than 1% of the transaction as money. So if it's $100, we only make 50 cents out of that transaction as profit as a bank. And if we lose the money, we lose all the $100. So that's a big chunk of money, and it's very unproportional. Therefore, fighting the fraud and finding the fraud is so relevant. And we're going to talk about that further, but let's just split our data set into train and test sample with 20% for the test sample. And for a very simple model that I'm gonna create right now, I'm just gonna simply use only the numeric variables that I have on my data set. And if I use accuracy here, what I see is that my prediction is like 96% in this simple model, 96% correct. Is that good? 96% on the train and 96% on the test. Is that good? It looks like a good model, right? Well, no, guys, it's a terrible model. Why? It's because the rate of fraud is only 0.038%. Therefore, if we classify everybody as a fraud, as a non-fraud, as a good transaction, this simple model of saying nobody's a fraud gets 99.96% correct. So our model is really terrible. Therefore, to start with, accuracy is not a good measure to evaluate these models at all. We need to do something else. So what we're going to use instead, we can use metrics that do not depend on the balance of the data. So Gini and KS are good ones for that. You can see the video about what Gini and credit and KS are in here, okay? But in any case, I'm gonna use my support package here and gonna calculate the Gini on this data set. So the Gini is 0.73 in the train and 0.72 in the test. That means, well, it's not as good as 99%. However, we have a point to start and improve it. And as you can see here, the confusion matrix currently is this one. And if I had to explain what the ROC curve is, what basically that is the calculation if I go changing the cutoff in here. So let's say the cutoff is 10%, 20%. Instead of getting the 50% as the cutoff, I calculate the cutoff being the probability being 10%, 20%, 30%, 40%, and go and further. And then what I'm calculating here is the area here. That's for the Gini, okay? And with that, I can calculate a metric that is independent of the actual cutoff and the actual proportion of the two, because I have the proportion of corrects and the proportion of incorrects in here. And also I can calculate the KS. That will take a while, so I'm going to pause it. That was the Gini that you can see in the video. The KS goes from 0 to 1, meaning 1 meaning 100% separation, and 0 meaning 0%, like something that is 3% 2% probability of being fraud. That is a very high probability, actually. 5% is very, very high, and you should block that transaction or call the person right away. So something like 0.5% probability, that's like probably that's not so high, but it's still, but like 0.2%, that's not high. But anyway, so, but it's not 50%. 50% is well high. Professor, a part of everything that we've seen already on the hyperparameter optimization and then selecting features, what do we have from statistics that we could use for fraud? Well, PSI is a good thing. It's a metric that you can apply to basically to see the difference between the actual and the expected when you get the two population, the train and the test. Why? Because fraudsters, they try to mimic, or they either try to mimic the fraud behavior or the non-fraud behavior, or they do something really strange. So you have the two extremes. So when you calculate the PSI, what should be the normal proportion and the bad proportion, the expected proportion, sorry, you either, on fraud cases, you either have a big number or a very small number. The guy is really trying to mimic the behavior, or the guy doesn't care. So those are two modus operandis that happen everywhere. So calculating the PSI for a variable with the expected behavior and the actual behavior, it's a good variable. So it's a good idea to do that. And so we can see here that there are some variables with PSI very small, very, very small. That's weird. We can look at for fraud, we have to look the small numbers and the big numbers as well. So the biggest ones, we have to look at them as well because they can be weird. So fraud, we have to look the extremes, and we also should look at the information value. So information value is a metric that, like it's like feature importance from random forest. If you are aware of feature importance from random forest, keep that. Don't come for information value. But information value is one that comes from the statistics. And here, same idea. In fraud, even information value or feature importance, you have to look the small numbers and the big numbers as well. Here are the two together. Finally, I'm measuring the Spearman correlation among the variables, and I'm putting all them together, the PSI, the IV, and the correlation, to actually have few information about the data set. So what's the importance of that variable to predict? What's the stability of that variable? Is that variable correlated with another? So with those things, I can actually decide which variable to remove and which variable to keep. So for the fraud detection game, this is a starting. One could change those metrics or even use genetic algorithm instead.